All right. Hello, everyone. So our last lecture is about oxidation reduction reactions. Oxidation reduction reactions, also called redox reactions for short, are reactions in which one element is going to be losing electrons and another element is going to be gaining electrons. Okay, so these are chemical reactions where actual electrons are being swapped between two different species. The compound that's losing the electrons is known as being oxidized, or oxidation is losing electrons. And gaining electrons is known as reduction, right? Gaining electrons is reduction, going down, right? And the reason that the terminology is the way it is because electrons are negatively charged, right? So if something's being reduced, if it's gaining electrons, its charge is going down. Okay, so that's a good way to think about it. So sort of pictorially, this is an example of an oxidation reduction reaction that takes place if you take a piece of zinc metal and you dip it in a solution of copper ions. What you see is that, okay, so again, we're starting with copper ions and zinc metal here. The copper will actually steal electrons from the zinc. So then copper goes from being a copper 2+ ion to just being copper metal, going from having a positive 2 charge to having a neutral charge, which is the same thing as, copper metal, copper solid. Okay, so it's stealing those 2 electrons from the zinc metal and going from being an ion to being just a metal. And in the process, because it's taking 2 electrons away from neutral zinc, zinc goes from being zinc metal, oops, that's not what I wanted to get rid of, goes from being zinc metal to now the zinc 2+ ion. All right, so there's an exchange of electrons that happens between zinc metal and a copper ion that creates copper metal and a zinc ion. And so what happens is if you leave this strip of zinc in there for a while and the reaction progresses, you now have a solid piece of copper, right? Your copper metal that's formed sitting in a solution of zinc ions, right? What was formerly the zinc metal now becomes a solution of zinc ions, and what was formerly a solution of copper ions becomes copper metal. And this happens because of a redox reaction, because of a transfer of electrons between the two species. All right, so we're going to learn these rules for calculating oxidation numbers for elements in a reaction. And there's going to be, it's like 9 or 7 rules, something like that, which is going to feel like a lot at first. And so this is a thing, just like when it came to naming ionic compounds, many of the things that we learn in chemistry are these kind of rule-based tasks, right? Determining whether a compound is soluble or insoluble given that chart. You had to sort of know how to use it. What I'm going to say is it's going to seem like a lot when we go through it. Practice, 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 okay? Because once you get the hang of it, it's really not too bad, but it's one of those things that looks really intimidating from the outset. All right, so we're going to go through these different rules step by step, do some examples ranging from simple to difficult, and then by the end we'll be able to sort of use that whole set of rules here. Okay, so this is all about calculating an oxidation number for an element. It's kind of a measure of how many electrons are living on that particular element in this reaction. So the first rule is that any element in its elemental form, the oxidation number is 0. So what do I mean by its elemental form? I mean, if you look, let's pull up a periodic table here. If you look up on a periodic table and you pick any element, let's just pick a random element here, aluminum. Its elemental form is what you would find it all by itself. So this case, it would be aluminum solid, right? Aluminum metal is the elemental form of aluminum. The ones that are tricky, and we talked about this a little bit at the beginning of this chapter, are going to be the diatomic elements. right? So there are 7 of them. It makes a 7 on this side of your periodic table, and then you have to remember to include hydrogen. The elemental form of these elements would be their diatomic state. So for oxygen would be O2 gas. That's the elemental form for oxygen. Okay. Yeah, so this is what we mean by the elemental form. Basically, when you find the element all by itself, that is it in its elemental form. All right, so if you have an element that's in its elemental form, its oxidation number is 0. So our goal is going to be to take a chemical reaction like this, take each species and assign its oxidation number. We can assign it for zinc and copper metal because both of them are found just in their elemental form in this reaction, right? So the oxidation number for zinc would be 0 and the oxidation number for copper would be 0. Okay, so that's rule 1. If the element is in its elemental form, its oxidation number is 0. Rule 2 is going to be that the oxidation number of any chemical species must sum to the overall charge of that species. Okay, so if we have a copper 2+ ion, that means that the oxidation number is 2+ for that copper ion, right? Because its oxidation number has to be the same as the overall charge on that ion. For zinc, if it's a zinc ion, zinc 2+ ion, that will also have an oxidation number of +2. So in this chemical reaction, we can see that this is an oxidation reduction reaction because the species oxidation numbers are changing, right? Zinc is going from being neutral to having a +2 charge. So it is losing 2 electrons, it is being oxidized. And copper is going from having a +2 charge to being neutral, so it is gaining electrons. So let's say gaining 2 electrons. So it is being reduced. Remember, gaining electrons because they have a negative charge, that's being reduced. Oxidized is losing, in this case, 2 electrons. Okay. Okay, so this is going to be the master cheat sheet of rules here that I wanted to, so we're going to go sort of through each one of them. I'm going to have a list of examples here and we're going to fill them out as we can, as we encounter that particular rule. Okay, working up to what is going to be sort of the most difficult, which is these, these polyatomic ions. All right, and this is not L. I don't know how that happened. This is AQ. Have to fix that. Okay. So again, the first rule was that the oxidation number of anything in its elemental form is 0. Rule 2, sort of restated a little bit differently, this is a simpler way of stating what we were talking about before, is that monotonic ions have the same oxidation state as they do charge. Okay, monotonic ions, same as the charge. So what do I mean by that? I mean, if I have a sodium ion, its oxidation number is +1 because its charge is +1. Likewise, if I have a chloride ion, its oxidation number is -1 because it has a -1 charge. Monotonic ions. These are the simplest ions, basically not a polyatomic ion. Okay. And so then if you have a compound like sodium chloride, you have to know that this is composed of a sodium ion with a +1 charge and a chloride ion with a -1 charge. So the oxidation numbers would be +1 and -1. Okay, so you're going to need to know the same sort of like rules that we used for our forming ionic compounds. That's going to come into play here. So if you weren't very good at ionic compounds when we first went over that, it's a good idea to go back and review it because it's going to be very difficult to do these types of problems without that knowledge. All right, and so I'll remind everybody real quick. We can look at the periodic table and tell what the charge is on these monotonic ions. Everything that lives in column 1 has a +1 charge. Everything that lives in column 2 has a +2 charge. For the transition metals, you have to either be told what it is in the name. So for example, iron 3 chloride would have a +3 charge on the iron. That's what that iron 3 means. Or if you were given a formula like FeCl2, you would have to know that each ion of chloride has a -1 charge. And so that's a total charge of -2, which means that the iron in this case would have a charge of +2. Okay, so remember, this is all stuff that we went over when we did the ionic compounds lectures. But yeah, that's going to be important for this chapter. If we work from the other side of the periodic table, the noble gases do not like to form ions. The halogens will form ions with a -1 charge. Keep on moving over. This column is a -2. And whenever we encounter it, although it's pretty rare, this column is a -3 charge. Okay. All right. So let's see if we can't knock out a few examples based on just these two rules here. All right. So again, step 1 is anything in its elemental form. Notice what we're going to do here is we're going to first calculate the oxidation number on the element and then its contribution to the total charge. And I'll show you what I mean by that as we come across an example. Okay, so hydrogen gas is in its elemental form. So this would have an oxidation number of 0, which then the contribution to the total charge would be 0. This sodium is in its elemental form, so it would have an oxidation number of 0. Contribution to the total charge is also 0. All right. What's importantly is that the sum of these oxidation numbers, they have to total the same sum as what you see in the compound itself. So when we're going to go over to sodium chloride here, this is a compound, an ionic compound that consists of monotonic ions. So we can assign their oxidation number based on rule 2. And importantly, the sum of these total contributions to charge have to equal the sum of the charge on this compound, which is 0, right? Our ionic compounds we construct in such a way that they have a net charge of 0. So again, sodium chloride consists of a sodium ion. I know that it has a +1 charge by looking at the periodic table, seeing where sodium lives. Chlorine has a -1 charge. I know that based on where chlorine lives on the periodic table. So the individual oxidation numbers are +1 and -1. And so the overall contribution to the charge is +1 and -1, which sums to 0. So that's good. So that can assign the oxidation number of that compound based on just that second rule. If we go over to magnesium bromide, this is also an ionic compound that consists of a magnesium ion with a 2+ charge and a bromide ion. Bromide ions have a -1 charge based on where they live on the periodic table. The net charge on this molecule, on this compound here, is 0. So that means that the total charge contributions will need to sum to 0. Okay. Because they are monotonic ions, their oxidation number is just simply going to be their charge. So +2 for magnesium and -1 for bromine. So this is where this comes into effect, where I'm going to account for the fact that I have 2 bromines. So its overall contribution to the charge is -2, whereas the magnesium I only have 1 of, so it's +2. And indeed, those do sum to 0. Okay. See another typo here I'm going to fix real quick. Should be HCl. Okay. All right, so now we got to move on to some of the other rules in order to assign these other the oxidation number of these other compounds. The oxidation state of fluorine is always -1 in compounds. What do I mean by in compounds? So basically, if it's F2 gas, that's fluorine in its elemental form. Its oxidation number will be 0. Any other time you find chlorine, I'm sorry, not chlorine, fluorine, its oxidation number will be -1. Okay, so if we go in here, we can go ahead and assign some of these oxidation numbers for some of these compounds, because we know that fluorine will have to have an oxidation number of -1. If there's 4 of them, the overall contribution to the charge will be -4. This one doesn't have fluorine in it, so we'll have to come back to that. This one doesn't have fluorine, so this one also has fluorine, so I know its oxidation number is -1. Overall contribution to the charge will be -2. Okay. All right, the next 2 rules here, let's look at. The oxidation number of hydrogen is +1, and this is where it gets a little tricky, unless combined with a metal. Okay, so hydrogen is almost, well, so first of all, H2 gas, this is hydrogen in its elemental form, so its oxidation number would be 0. Any time you find hydrogen in a compound, its oxidation number is going to be +1. So for example, HCl, the hydrogen's oxidation number is +1. However, if it's in a compound with a metal, an example of that would be NaH. Its oxidation number isn't going to be +1. We're going to have to use rule 7 to figure it out. So let's wait until we get to rule 7, and then we'll work on doing something like sodium hydride. So actually, let's put that as an example here, and we can come back to it. Okay. The oxidation number, so the next rule that we're going to look at is that the oxidation number of oxygen is -2 unless it's in a compound with fluorine. Okay. Now, these kind of seem like specific rules. Fluorine's -1, hydrogen is +1, oxygen's -2. It might seem like that's a lot of information to remember, but remember, we can tell that just by looking at the periodic table as well. So it's not really anything different than what we saw with ionic compounds. It's just these elements will also have these same oxidation numbers when they're in covalent compounds, right? So if we go back to our examples here, H2O is a covalent compound. So we wouldn't say that it's composed of hydrogen ions and oxide ions because it's covalent, but it has the same sort of rules that we would expect as if it was an ionic compound, where the hydrogen's going to have a +1 charge and the oxygen's going to have a -2 charge. Okay, that's what those rules were just telling us, as well as the rule for fluorine. In this case, this also works out as it should because the net charge on a water molecule is 0, and indeed those do sum to 0. Okay. Yeah, so we can actually also, based on rule 2, we can tackle this one here. These hydrides, these are weird ionic compounds where you have a sodium ion, much like you do always, but the hydrogen ion in this case has a charge of -1, right? Because it has to counterbalance that sodium ion. So this is a charge of +1. We could do the hydride as -1, but let's wait, and we're going to use rule 7 because I wanted to show that as an example as to how we can do that. Okay. Notice here, oxygen, we said it almost always has a oxidation state of -2. The exception is when it's in a compound with fluorine. So because it's in a compound with fluorine, we're going to have to wait until we get to rule 7 to figure out what its oxidation state is. Okay. Hydrogen is +1, right? And then oxygen, when it's not in a compound with fluorine, as is the case with this example here, its oxidation state is -2. So the overall contribution to the charge, I'm going to have to take this -2 and multiply it by 4. That would give me -8. Okay. Excellent. Okay. So let's keep going through these. The oxidation number of all the other halogens is, as you would expect, -1. But again, now, unless you're in a compound with oxygen or fluorine. So what you sort of see here in these rules is that rule 1 is more like it beats out all the other rules. So fluorine has an oxidation number of -2. Yeah, or I'm sorry, of -1. Yeah, unless it's in its elemental form, because that was rule 1. Likewise, fluorine is -1. Oxygen is -2 unless it's combined with fluorine, because that's rule 3, right? So you can see how the higher it is on this list, the more important of a rule it is. Okay, but the fact that the halogens have an oxidation number of -1, that's not too terribly surprising, because on the periodic table, that's what they would have if they were in an ionic compound. Turns out that that's also what they have if they're in a covalent compound, as long as it's not with oxygen or fluorine. So if we go back to our list over here, we can see that we can now assign this chlorine as -1. And indeed, those total charge contributions sum to 0, as they should, because the net charge up here is 0. Okay, so now we get to this infamous rule 7 that we've been talking about. All oxidation numbers are assigned as follows. So this is when you don't know based on these rules here. So there are going to be some elements where we have to figure it out based on the oxidation number of everything else in the compound. And that is, the rules are basically the sum of the oxidation states for a neutral compound must equal 0, and the sum of the oxidation states for the polyatomic ion must equal the charge on the ion. So that's already kind of what we've been doing here, is making sure that our total charge contributions sum to the overall charge on the molecule. But that's how we're going to figure out the oxidation state for the elements we don't know. So again, taking this compound as an example, we know what fluorine was based on our rules. It has to be -1. So we know the charge contribution from the fluorine in this case is -4. Well, these all have to sum to 0, because the net charge on this molecule is 0. So then I can work backwards to figure out what carbon is. This is going to be a +4. Since there's only one carbon, the oxidation state is then +4. Okay, so that's how we have to work backwards using that rule. Same thing down here. Oxidation number of oxygen is usually -2 unless it's in a compound with fluorine. Fluorine's always -1. So we have to figure it out based on the fact that these two should sum to 0, which means that this number has to be +2. Since there's only one oxygen, the oxidation state of oxygen in this compound is +2. Okay. Same with our sodium hydride. We could figure this out by the fact that these have to sum to 1, or I'm sorry, have to sum to 0. So the oxidation state of the hydrogen is going to be -1. It's actually always -1 in these hydride compounds when hydrogen's bound to a metal. All right. And then things get tricky when we have a polyatomic ion, because it has a net charge of 3. Every other example that we've done has a net charge of 0. This sulfate ion has a net charge of -3. So this all has to sum to -3, which means that the contribution to the charge from sulfur has to be +5, right? 5 minus 8 is -3. There's only one sulfur, so that's the oxidation state of the sulfur in that compound. Okay, so we're going to do a bunch more examples, because I know that this is tricky. Again, step 1 is to figure out what elements you can fill in just based on the rules that we know. This is a ionic compound that takes place between a potassium ion and a permanganate ion. This particular polyatomic ion isn't one of the ones that I told you had to know. But remember, there are ones that I did tell you that you have to have memorized, and I'm going to expect you to know those for the exam. Those were hydroxide, nitrate, carbonate, sulfate, and phosphate. So you should be able to calculate the oxidation state for all those elements in those ionic compounds, all right? And in particular, remembering these charges is going to be really important to calculating it correctly. So this is a permanganate ion. It isn't one of the ones that I told you that you had to know, but FYI, okay? So telling you what it is now, we should be able to work through it. So first of all, because this is an ionic compound and I have my monotonic potassium ion, the first one that I can fill out is the fact that the potassium ion has a +1 oxidation state, and its overall contribution is going to be +1. Okay. The next thing that I can figure out based on those rules is oxygen. Oxygen almost always has an oxidation state of -2 unless it's in a compound with fluorine. We're not in a compound with fluorine, so the oxidation state of oxygen would be -2. The contribution to the overall charge would then be -8. So now I can work backwards to figure out what that manganese ion is, because all of these have to sum, right? So these all have to sum to 0 down below here. So I have 1 -8. That means that I would need to have a +7 in order to have that sum to 0. So the oxidation state on the manganese ion is +7. Or the manganese atom is +7. All right. Let's do a few more here just to kind of hammer this home. I guess we already did the sodium hydride, right? So that was +1 and -1. The hydrogen is usually +1, but if it's in a compound with a metal, it's -1. All right, so let's go through and figure out the rest of them. So the next rule, so nothing's in is in the elemental form, right? So nothing applies to rule 1. There are actually no monotonic ions here. These are all covalent compounds, right? Remember, how can I tell if it's a covalent compound? Let me get rid of all these markings real quick. Where are both elements in a covalent compound going to live? They're both going to live on this side of the periodic table. Right? These are the non-metals. So if I have a compound with sulfur and oxygen, or carbon and oxygen, those are covalent compounds. All right, so rule 2 isn't going to apply. Nothing here is a monotonic ion. But importantly, and the one that you can see is probably one of the most important rules, if you forget every other one, is the fact that oxygen is -2 in these covalent compounds. So you can see each one of these covalent compounds will have oxygen being -2. There's this exception if it's in a compound with fluorine. Truthfully, the only compound that I can think of that contains oxygen and fluorine is this guy right here. All right, so as long as it's not this, you should know that the oxygen has an oxidation state of -2. I guess the other exception, not quite an exception, but is when you have O2 gas, which will have an oxidation number of 0 because that's in its elemental form, right? But if it's not these two examples, then it's going to be an oxidation state of -2. So this is -4, the overall contribution to the charge, because it's that -2 times the fact that there are 2 oxygens. And this has to sum to 0 because the net charge here is 0. So this would be +4 over here. Okay. If we move on to the carbonate ion, the contribution to the charge is going to be -6 because I have 3 and they each have a oxidation state of -2. This has to sum to the net charge on the molecule, which for a carbonate ion is -2. So what -6 gives you -2? That would be +4. Okay. Our last example, oxygen, we have 5 oxygens that each have a oxidation state of -2. So this is -10. This has to sum to an overall charge of 0. This is a neutral molecule. So this is going to be +10 for the nitrogens. But now working backwards, I have to account for the fact that that's the total contribution to the charge, and I have 2 nitrogens. So each nitrogen would have an oxidation state of +5, right? I have to take that 10 and divide it by 2. Okay? So that's how we calculate oxidation states for compounds. All right, so there are multiple types of redox reactions. And so we want to be able to categorize these reactions. We learned about 2 types of reactions already. They were not redox reactions, but those were precipitation reactions and acid-base reactions. Now we're going to learn a few other types of reactions. These all fall under this umbrella of redox reactions. I'm not going to go through step by step to do the oxidation numbers. It's a good idea to pause the video and work through these, especially this first example here is pretty tricky. So if you can get that, that's awesome. Yeah, the other ones are good too. But bottom line is, I'm going to go through it kind of quickly, but you want to be able to calculate oxidation states for the compounds that are in a reaction. Okay. So in this case, zinc is 0 because of its elemental form, same with copper. The sulfate ion and these copper and zinc compounds with the sulfate ion, I would have to work out based on the rules that we discussed. Importantly, how do we spot that this is a redox reaction? Because the oxidation state of zinc is changing from 0 to +2. Likewise, the oxidation state of copper is changing from +2 to 0. So anytime you have a change in oxidation state from one side of your chemical reaction to the other side, that is indicative of an oxidation reduction reaction, a redox reaction. Notice that the sulfate didn't change at all. It was just sulfate on both sides. It's cool. It's not that everything has to change. If any element changes its oxidation number, it is a redox reaction. So these are called single displacement reactions because you can see that my zinc displaced my copper from the ionic compound, right? I effectively swapped my metal and my cation. Okay. The next type of reaction is a combination reaction. This is anytime you have multiple reactants coming together to form a single product. Right, so generic kind of reaction, A plus B gives you AB. These are combination reactions. These are also going to be redox reactions, and we can see using this example, these are these 2 elements in their elemental form, and they come together to form an ionic compound. Okay. Decomposition reactions are the exact opposite of combination reactions. This is where you have A, B decomposing into its individual components, A and B. These are also redox reactions, again, because we're changing the oxidation state from the one side of the reaction to the other side, from the one side of the chemical equation to the other side. I guess just to take a step back and give you what would be the generic form for our single displacement reactions, that would be something like A plus BC gives you AC plus B, right? Importantly, where that name comes from is the single element is being displaced there. And then the last one is kind of a specific type of reaction. It's called a combustion reaction. This is any reaction where you have some organic compound, some covalent compound that's reacting with oxygen to produce CO2 and H2O. The hallmark of the combustion reaction is that the 2 products are always the same, CO2 and H2O. Okay. These are combustion reactions. And if we went through and calculated oxidation states, it's not a bad idea to pause the video and see if you can't do it yourself. But I'm just going to give it to you real quick for the interest of time. We can see that we have our carbon is changing its oxidation state from -4 to +4. And then the oxygen is changing its oxidation state from 0 to -2 in these 2 compounds, right? So the combustion reactions are also examples of redox reactions. So being able to go through and categorize these reactions according to those 4 categories that we just discussed. Okay. Let's see if we can work our way through these. Here we have two reactants combining into a single product. So these would be combination reactions. Here in this next one, how I'm going to sort of go through it is I'm going to immediately be drawn to the fact that my products are CO2 and H2O, and that means that this is a combustion reaction. All right, in my next example, I have a single reactant that's being broken down into two different products. So this would be a decomposition. That doesn't look right. How do we spell that word? Composition. Okay, I'm obviously a scientist and not a speller. Composition. Okay, so the next one's a little bit trickier. I have silver that starts out as a solid and then it makes its way into this covalent compound, ionic compound. And I have this copper that is in an ionic compound and then gets displaced into being a single element. So this is a single displacement reaction. All right, for the next one, again, I'm going to be immediately drawn to the fact that I have CO2 and H2O as the product. So that lets me know that this is a combustion reaction. Okay. For my next example, I have a single reactant being broken down into two products. So this is a decomposition reaction. All right. For the next one, it's a little bit trickier, but if I'm going to go through it, I'm going to notice that magnesium starts out as a solid and then makes its way into this ionic compound, and zinc starts out in an ionic compound and then makes its way into being solid zinc. So this is a single displacement. And then for the last one, I can see that I have two reactants combining into a single product. So this is what we called combination reactions. Okay, so these are our four categories of reactions here: single displacement, combination, decomposition, and combustion. You want to be able to identify those just like we did in this example problem here. And again, these all are redox reactions. They all fall under that umbrella of redox reactions. So for any one of these, you could go through and calculate the oxidation state of all the elements involved, and you would see that their oxidation state changes from one side of the chemical equation to the other. Importantly, precipitation reactions and acid-base reactions that we discussed in the last lecture, those are not redox reactions. So if you went through and calculated oxidation states for all the compounds in those types of reactions, you'd see that they don't change from the reactant side to the product side. The last thing we're going to talk about, and this is just quick terminology that we need to know. This is this idea of whether or not a reaction is endothermic or exothermic. The back end of those words, thermic, right? So thermo, we're talking about temperature here and specifically heat. Reactions that consume heat are called endothermic reactions. Okay, this is a reaction that actually will absorb heat from its surroundings as it's going on. So if you were to hold in your hand one of these endothermic reactions, you would feel your hands getting colder because they're stealing the heat as they're going. So this would be we kind of think about heat being on the reactant side of these types of reactions, of these endothermic reactions. Okay, because heat is being consumed. If we go, the flip side is an exothermic reaction. These are reactions that produce heat. They release heat. Okay, so we put heat on the product side of the reaction. Okay, combustion reactions produce a lot of heat. All right. A simple combustion reaction would be like if you were to light a lighter. It's not methane, it's likely butane or maybe something a little bit larger, but you're going to have this organic compound that's reacting with oxygen. And we all know that that produces heat, right? Those flames produce heat. Those are examples of exothermic reactions. Okay, so these two terminologies, endothermic and exothermic, are important to have in your brain. Again, endothermic reactions consume heat and exothermic reactions produce heat.